Okay, Mariah, we are on page 264. We've already gotten started. I'm not going to go back. If you need help on the first page, let me know. I'll discuss it with you. We are on example 1, page 264. We're going to try to find the area under a curve of a function that we're very familiar with, which is v of t equals t squared. And we're going to try to find the area after time from 0 to 3. So if you can see the picture there in example 1. So we actually have a knowable function, and we're going to talk about how we might use little tiny rectangles to approximate the area. Okay, because it's a curve.
Okay.
So here is that piece of parabola, which is v of t equals t squared. And we're going to go out to 3, which I'll say is right there. And so we draw a line up to there, and what we're looking for is this area underneath here. And if this is a velocity curve, which it is, this should tell us how far an object traveling at this velocity, this velocity curve is going faster and faster and faster and faster, should tell us how far he went after 3 minutes or 3 seconds.
What are our units on the y-axis?
I don't know, I don't care. We'll say meters per second. Okay?
Not units, like 1, 2, 3, 4, 5, 6, 7, 8. What's our scale?
Well, up here would be 9, because 3 squared is 9.
Okay. I wonder how accurate it would be if we just made 27 and cut them out. All right.
Take a look at this. Do you understand we're trying to find the area under the curve, and the only method that we have is to split it up into rectangles in this case, into geometric shapes that we can find the area of, and then we'll add them all together. Does that sound good?
Yep.
If we were to split this up into 12 pieces, I'm going to only do 6 because I don't want to take forever on this. If I were to split it up into 6 pieces, then I would be looking at rectangles that end here, and here, and here, and here, and here, because 3 divided by 6 is a half, so each interval's got to be a half a unit. Yep. Do you agree? So this right here is, I'll go ahead and write it down, this is 1 half, this is 3 halves, this is 5 halves.
Ms. J, when you do this, is it better to have your rectangles go above the curve or stay underneath?
We'll talk about that. It's coming. It's coming.
Do it half.
So if I take these markers and draw right straight up to the curve in each case, we don't actually have rectangles. We have what we call partitions. And we have 6 of them because we're partitioning them at each half unit. Partitions. Do you understand what I mean by that?
Yeah.
Okay. Now, the question becomes, do we want to draw rectangles that are above the curve, or do we want to draw rectangles that are below the curve, or do we want to draw rectangles that are a little bit of each?
Can you alternate a little bit of each, but undo each other?
Alternate.
You can alternate, but then you've got to do you have to do each individual rectangle. If we do them all the same, we might be able to see a pattern where we can evaluate them quicker.
Well, we do one that's half.
So just listen. I want to draw the first one. I want to do it as what we call a right rectangular approximation method. The abbreviation is RRAM. Right rectangular approximation method. We'll refer to that as RRAM. And if we do a left side, it will be LRAM. And if we do a midpoint, it will be MRAM. Now let me show you how you draw each of them. And then, depending on which RAM they ask you to do, you'll know which way you're going. If I was to do an RRAM for this one, it means go to the right side of your first partition and make a rectangle using a rectangle with that height.
So is our first position 0?
No, we'll see in just a minute. But this uses the right side as the height of the rectangle. Do you see what I'm saying?
Oh, okay.
That's the height of the rectangle. If I use this as the height of the next rectangle, the right side of that partition, the rectangle is this one. You see?
Yeah.
And the same thing here, and the same thing here, and here, of course. And if we do this on this particular curve, if we do that, it's going to be, and find those rectangles, it's going to be an over approximation.
Yeah.
Do you agree?
Yeah.
All right. We will do one of these in just a minute. But I wanted to show you how to draw these because it's harder than you think when you actually have to do it on a weird one. We'll do that in a few minutes. But if instead I do a left, if I do an LRAM, that means I go to the left side of the partition and draw a rectangle, in which case that would have no area. This one would have this for its rectangle right here. This one would have this, and this, and this, and this, and that would be an under approximation. In other words, we would be leaving out the area of that, and it's not really a triangle, it looks like it, it's pretty close. We'd be leaving out that, and that.
Well, if it's,
So it would be an under approximation.
just approximating, can't we just find the area of those rectangles?
Yes,
Can't we assume that those are?
that's how we would do it if we were doing a left rectangular approximation method to find this area.
With the triangles, like, because it's just an approximation. Can't we just find?
But those triangles aren't really triangles, they're
Yeah, but
curvy.
it's just an approximation.
So go ahead. Go ahead and try it.
But then you have.
And you will get closer, and they have done that. We're not gonna use that method. We're talking about only rectangles for right now, okay? So if I get rid of these so that I can draw the next one, the midpoint, what we do is we go to the middle of the partition, go up to the curve at that point in the middle of the partition, and go out right and left. Can you see that would be a pretty good one? Because this would be over, we would be filling in this area, but we would be leaving out this area, and they're almost the same, but they aren't exactly, because they aren't triangles. So if I went to the middle of the next partition and went up to the curve and then went left half and right half, I've got an over approximation with this and an under here, and they're almost the same. So this looks like a good method to me. You follow me?
Yeah.
Okay. If I went to the middle of this one and then I went over and over, middle, go right up to the curve and over, curve, and middle here. That looks like it's not too bad. Now let's actually find the area of those rectangles. This would be the midpoint approximation method drawing. And so what we want to do is actually find the area of each of these green rectangles. I'm going to take these out. This was just to show you go to the midpoint and then up. But as we're talking about these rectangles right here.
116.
Hang on. How do we find, well, first of all, what is the width of this rectangle? What's the width of this one? And this one? That's the reason why it's kind of nice to make partitions that are the same width, because in each case, we're going to be taking 1/2 times the height, based on height, right?
So.
Then we just go, yeah, 6 hours.
What determines the height? The function at these values right here.
So B of
So I would say instead of height, I would say, this is, so you get used to the notation, it's 1/2 times f of x I. The function evaluated at, this would be x1, this would be x2, this would be x3. Do you see what I'm saying?
Yeah.
And if we wanted to really make this correct, that 1/2 belongs only to this picture. Instead, in a general way, we say that the area of the rectangle is going to be delta x.
Oh,
The change in x, which
so
is
your
this
program
width.
does this for us. That's cool.
Yeah, it does.
Very kind.
But this is the width of the partition, the change in x. That's 1/2 in our case. Are you with me?
Yep.
That's the width of the partition. And this is the function evaluated either at
At the X is
0, 1/2, 1, 3/2, 2, 5/2, and not 3. If we were doing the right side, actually it would be 3. If we were doing the right side, we would use this as our x1, this is our x2, x3, x4. But I'm not doing that. I'm going to do this midpoint because we like it better. It seems to be a better approximation. That x1 is 1/4, right? This one is 3/4, 5/4, 7/4, 9/4, 11/4. You see it? Okay. So I've got the very first one. I've got 1/4 times 1/4 squared.
Which is.
I'm sorry, not 1/4, not
That's
1/4.
a half.
This is 1/2. This is the width of the partition, which is 1/2. But we evaluate the function at the midpoint of that first partition, which is 1/4. You follow me? This is the area of that first little rectangle.
Oh, yeah, because that's the function.
See, we have to go up to the function, and the function value when x is 1/4 is 1/4 squared. Y'all see it? To that, we will add the area of the next one, which would be what? 1/2. That's the width of the partition.
3/4.
3/4 squared plus
1/2.
1/2 times.
5/4.
There you go.
Squared.
Plus 1/2, 7/4 squared.
Yep.
Plus 1/2.
Nine fourths.
9/4.
Even till 1/2,
So
and 11
till
fourths years
11/4.
have passed away since.
I freaking get what?
So that's how they used to do it.
Okay.
However, they did recognize that it could be written like this.
A summation of all that crap.
Of 1/4 plus 1/2
Squared.
Plus 3/4 squared.
Yeah.
And then they broke out their calculators
Nope.
and
They
plugged
just,
it in.
No, they did it in their heads.
Oh, wait,
Because
is this not
remember
a
they're
summation?
smart people like Sam wanted to be. Gosh dang it. Here, I'll stop you.
here's something else that they could have done to simplify things. They could have factored out
Oh, 1/4.
a 1/16.
That's what I meant.
Wait.
Oh, yeah,
1/16. Got it.
Whoa.
Every one of them is a fourth of some kind squared. So a 5/4, for example, is 5 squared times 1/4 squared. Do you agree?
So just take out 1/4.
Yeah.
And every one of them's got a 1/4 squared.
Yep.
So I could go a bit further. I could say 1/2, that's the 1/2 right there, times 1/4 squared, because they've all got that, times 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 squared plus 11 squared. That makes things a little bit easier. Does that make sense, the factoring out?
So it actually.
This would be 1/32, wouldn't it?
32,
Can
yeah,
you
1/32.
factor out a square?
No, you cannot.
Oh.
That would be 1 plus 9 plus 25 plus 49 plus 81 plus 121. And then they would grab their,
Calculator.
well,
Abacus.
it's somebody that you hired or abacus,
Their
yeah, whatever.
Abacus.
And add these up.
Slide over to the beach.
Can you do that in your head?
Wait.
I'm gonna guess that it's
130.
9.
Let's see. Let's combine similar numbers. 10.
I think it's gonna end up to be
10,
9.
49 and 121 is
286.
286.
yeah.
Times
286 over 32, I'm gonna come over here.
which is 9.
286 over 32, obviously we can at least take a 2 out. What would this be?
150.
143 over 16. What is that as a decimal? Now grab your calculator.
8.9375.
Oh, look at that. Kylie owes me $5.
It's not 9.
Yeah, but it's close enough.
Explain to me
Yeah,
again.
8.9 squared.
It is actually 9.
Because each one of these things, take this one for example.
Yeah,
That's the
it should be
same
9.
thing as 5
Because if
squared
you
times
add
1/4
right,
squared.
Yeah.
So and every one of them's got a 1/4 times whatever that.
Yeah, okay.
Take it out.
130
But
cubed.
I have to take it out squared.
Plug in a 3. And then like 9 times a third.
Well, 3 and then you have to subtract the
Yes.
zero.
So every one of them's got a numerator squared times 1/4 squared, so I just factored out 1/4 squared. And that left me with the numerator squared to be summed. You know what I'm saying? All right, so we get 8.95. What do you think the true value is? 9. It is. Now, why was it an underestimate? Slightly.
Because our right end is gonna grow faster.
Yeah.
Because this
And on
piece
left
of
hand.
each one is slightly bigger than the one next to it.
But not in our rectangles.
Because it's free-handed, you dog.
That's not what I meant.
All right.
I meant our rectangles didn't compensate for that.
Look at the very bottom of page 265. Look at the very bottom of page 265. Can you see those drawings and what they're representing?
Yes.
Left ram, middle ram, right ram. Those rectangles that are drawn. And so the left one's gonna be an underestimate if we have this kind of curve. The next one's gonna be probably the closest we can get for fewer rectangles. And the next one will be an overestimate. Turn the page.
Woo.
They show you, and I'm not going to do this, they show you how to figure that for L, M, and R, but what I want you to notice is the totals at the end.
Those are garbage.
With only a few rectangles, the left ram was severely underestimated. But we knew it would be an underestimate by a lot. There was a lot of wasted space there. And the middle ram was what we got, which was pretty close to the true value, which is 9. And the R ram was quite a bit over. We expected that. Okay, you with me?
Yep.
With the 11.375?
Are we gonna go into a why left arm?
Don't ask me questions, I'll take you where I want you to go. Here we go. If n were those numbers in that table that you see in the middle of the page, if we had 6 rectangles or 12 or up to 1,000, I want you to notice the values of the 3 rams keep getting closer and closer and closer and converging on the true answer. So see if you can extend your thinking and conceptualness a little bit farther. Do you understand my statement when I say, in this process that we've been studying for the last little while, the limit as n goes to infinity is the area under the curve. Not an approximation, it is the area as n goes to infinity, n being the number of partitions. Does that make good sense?
Uh-huh.
That was the idea, that was the leap in the 17th century for calculus, because they had been doing this stuff since Archimedes' time. This calculating of rectangles or geometric shapes. But it was the limit idea, letting n go to infinity, and the study of and considering things about infinity that led to what turns out to be not ever an approximation, but an exact way of calculating these things. But for this chapter, this section, we will continue approximating. So what I want you to do now is to grab those programs that I got for you, and let's see if we could get this number with the program. Some of you have already done it. That's fine. You go to your program list, you grab Riemann, hit enter, and the very first thing it says is enter f of x in y1.
Wait, no. This is.
Hit enter.
It does.
You gotta get the program started. So the moral of this little story is, because I had you do this first, put your stuff in y1 before you start Riemann. Okay? And how do you get out of there to do that? Quit. Okay, and it says done, so you can clear your screen now. Go to y1 and put in there what? X squared. Because we're trying to duplicate this with the program. Okay, so we go x squared. Now get out of there, go back to your home screen. Now start Riemann. Hit enter, and it says, do you want to continue now that you've, because you could hit no, which means, oh yeah, I forgot to go put it in y1. You could hit 2, the number 2, and it would just quit, and it would give you a chance to put it in there. So now we want to continue, so we hit 1,
Pictures, yes.
enter. Draw pictures, yes, I would always like to see the picture, thank you. And it says left endpoint, that would be 0.
And
Right endpoint, 3. And the next question it asks you is,
4.
do you want to use left, right, trapezoids, or midpoints?
Trapezoids.
No, we're not doing trapezoids today. Pick one of the 3 we're studying. Midpoint, so hit 4, enter. And then it says n, and that means how many partitions? How many did we decide on? 6. We decided on 6. We're trying to match it, so we choose 6 for 6, and then we hit enter, and it draws you a graph. There's your, it's pretty cool. Pretty cool, right?
I feel like a little kid. That's what I just drew.
I know.
Wow.
I feel like it's Christmas time. Now, that was really cool. Are you over the coolness?
Yes.
Look in the upper right-hand corner and look at the dots. That means it's been solved by the program. What do you do to get it unsolved? Hit enter. And it will take you back and tell you what the value is.
I think that takes all I know.
That is so cool.
Does that make sense to you?
Oh, yeah.
Now, everybody, just for practice purposes, go and do the very same function, same number of partitions, do a left. Okay, left.
Oh, wait.
Whoa. Yeah, how do you get out of this?
Just hit
Yeah, you hit enter and it says change n. No. Change method. Yes.
Oh, you can do that?
Yeah, it's kind of cool.
My
So you
bad.
go back to your left rectangle and choose 1, enter. N is still 6. I don't know why it said
You want to do
change
left or right?
left. And it gets to the graph. Remember how you get out of this? You hit enter to get it to quit, stop stalling. It goes back to your home screen, 6.875. And isn't that what they got at the top of page 266? Now, just for the fun of it, go find your right. See if you can operate with this function.
Wait,
this
how do you
program.
do that thing just without going?
Hit enter again and then hit change method.
Enter.
We want to do a, which one this time?
2, right.
All right, which is number 2. So you hit 2, N is still 6, enter, and it does the right ones for you. Obviously an overestimate. Then hit enter to get out of the stall mode, and you get 11.375, which is what they got. Kind of nice.
Kind of partition. And then you could do these, do each one, and then average it and get closer to the actual.
Maybe. Try it. You can try it if you want.
I did.
Okay, and did you?
Yeah, it was like 9.0 something.
Sam.
Trapezoids is actually really close.
So what we learned from that is that the underestimate is a bigger underestimate than the overestimate is over. What we learned from averaging them and not getting the true value is we learned that an underestimate is a greater underestimate than the overestimate is an over one.
Yep.
Because the average would have come out to be 9 if it wasn't.
Never gonna
Trapezoidal.
Okay, listen up. I was gonna say, for the sake of batteries and your calculator, do not do any n values greater than 50. The book will ask you to, don't do it. It's a waste of time, it's not necessary for the concept development. Don't do anything greater than 50 for your n value. It'll take a while to do 50. Try doing any of the LRAMs or any of the RAMs that you want with n equals 50.
Sam, 1. This is midpoint 1.
So n's gonna become 50, and I'm gonna go ahead and do the right RAM, and you notice it's gonna be a really, really nice estimate. You hit enter, and you get really close to the 9. It's still an overestimate, but not by much.
Oh shoot, that is kind of crazy.
And is our partition.
It's coloring every.
N is our partitions, which is 50. Don't go more than 50 on n, okay?
Not like that.
Wait, so how many do we do? Like,
Don't do more than 50. I did 50,
Yours wasn't coming.
and I got that the right RAM was 9.272, and that's pretty close.
That takes me out.
this is gonna take me a while.
Yeah. Making your calculator do this is equivalent to, in the 17th century, hiring several people that were good mathematicians, good arithmeticians, to come in and calculate their particular rectangle with the function, find the value, and then have someone else sum them all up. And that happened that fast.
8.99.
They were called cipher rules.
So
They were
basically,
like bookkeeping.
your calculator is a group of people like this.
Yeah, we need 100.
Okay, here we go, folks. We're gonna take this a step further, and it's gonna take your concentration to do it, okay? I want you to look at example 3. This was gonna stretch your thinking on these ideas a little bit. We need to think together and try not to get distracted. Here we go. Shh. Just before example 3, it says, although the visual representation of RAM, approximation, focuses on area, remember that our original motivation for looking at sums of this type was to find distance traveled by an object moving with a non-constant velocity. The connection between examples 1 and 2 is that in each case, we have a function f defined on a closed interval and estimate what we want to know with a sum of function values multiplied by interval lengths, delta x and f of xi. Function values, that's f of xi, times the interval lengths, that's delta x. Because that's length times width, which is the area of rectangles. Many other physical quantities can be estimated this way. That's what we're jumping to now. This is a different physical quantity. Now, we all know how to find the volume of a sphere. That is not the issue. So get over it. We want to estimate the volume of a solid sphere using these ideas. So we're going to it for an estimate, and I know we can do better. Don't talk to me about that. We're going to estimate this to apply these concepts. Here's our deal. They've got a sphere to the left. Well, it kind of looks like a sphere. It looks like a 2D, kind of a tan colored circle with a center at the origin, radius 4. And what they're going to do in the next picture is they're going to slice that sphere up like a loaf of bread. Have you guys ever seen the artisan bread that they offer over at Rollins? They're just round.
Yep.
And they're kind of moundy in the middle. That's kind of like this, only this is a true sphere. And when you slice those, you keep getting bigger and bigger and longer pieces of bread, taller and bigger. Okay, well, that's what's happening here. We're going to slice this like a loaf of bread. And it says, if you'll count those, how many slices are we going to make?
8, 9, 8.
8. We're going to make 8 slices, and we're going to pretend, this is the estimate part, we're going to pretend that each slice is an actual cylinder. Okay?
Oh.
And then we're going to find the volume of each cylinder and add them up. But the cylinders, listen, the cylinder's height, once we pull it out like a record from like a vinyl, pull it out like this and lay it down, the cylinder's height from before we pulled it is delta x. You agree? That was delta x from the strips that we sliced.
Okay, yeah.
That was delta x.
Okay, yeah.
And the radius of the cylinder, once you pull it out and lay it down and sit like this, it's a short, fat little cylinder. The radius of it, when it was like this, is the function value. And the function is a circle.
So there's R squared.
Let me erase this and I'll show you what it is. But you gotta imagine what these cylinders look like and what values on them came from where? I haven't heard from you from a while, Jacob. I'm hoping you're not offended by shutting you down.
No, I just stopped paying attention.
All right, that's fine. It's whatever. Okay, so this is what we start with is a 2D circle. That's a really crappy circle. It's centered at the origin where this is 4. Okay? Now this is what, in a 2D fashion, before we pull the cylinders out and lay them down. Before that, what we're doing is we're splitting this up into 8 pieces, which means each half is into 4, like this. Well, actually, it goes all the way down.
Okay, there. Got it.
Okay? So if I were to pull, for example, this cylinder right here, if I were to pull that one out and look at it through the hole in it like this, the radius would be either this, or this, or this, depending on which RAM I decided to use. You want to do a midpoint RAM?
Yes.
Okay, that's fine. Which means that when I pull this slice out, it's going to be cut like this.
Yep.
Do you agree?
Yep.
And this one down here will be the same. We go to here, we go over like that, and over to here like that. And that is our slice of bread, our slice of sphere,
Whoa.
as it comes out. Now, what is the volume of this particular one that I have shaded right here? What's the volume of any cylinder?
Base height. 1/3 pi squared.
Let's call cylinder.
Pi r squared h.
Yeah, the area of the base, which is a circle, times the height. Okay, now remember, when we pull that one out and lay it down so that it looks like a cylinder,
H is delta x.
yes, H is delta x. It looks like this. This is delta x because it came from here. This is delta x. Well, actually, from here to here is delta x, right? And this is the r, but what? It's the function. In our case, evaluated at. This is 4. What is this?
xi. 3 halves.
3 halves.
Oh, like, okay.
Yeah, actually, I know. I didn't ask you that. And this is not delta x. It's 1. Yeah, the distance from here to here. This is 4. We're splitting this side up into 4 pieces. Delta x, this piece right here, from here to here is 1. And this location on our grid here is 1. This is 2. And this is 3 halves.
How do we find those 3 halves? Because they're each a thing of 1.
Because this is a circle of radius 4, so each one, if we're splitting it up into 8 pieces, then 4 of them are over here, which means they're each one unit. And we want to go to the middle of this particular one I'm talking about, which would be 3 halves. But what is x?
X squared equals 16. Y squared equals 16 minus x squared, so it's y equals root of 16 minus x squared. That's our function.
That's not what I'm asking you yet.
What are you asking?
Oh,
Is it just?
yes, I am asking. What?
Okay.
It would be the equation of the circle. Isn't that our function? And you're going, it would be the top half to make it a function, yes. But it's the equation of the circle in general, and since we're talking about the top half, we will take the positive aspect of the square root.
Y
So
equals
you have to
root.
do both.
Okay, so this was x squared plus y squared equals 16. You all agree with that?
Why are we only talking about?
Because we're talking, we
We
need a
just need
function.
the radius.
We need a
The
function.
radius can just be
And the whole
part of it.
circle is not a function. Okay. Besides that, I only want to know what the distance is from here to here, which is somewhere on the top half of the circle. Okay? I could do the bottom half if you wanted to go from here to here, but I need a radius, which has to do with from the x-axis up to the function, so I only need the top half. You with me? Okay. So solving for y gives me y equals plus or minus, but I'm only doing the plus, 16 minus x squared, which is what Sam's been yelling at me for a while. He's right, but I wanted to show the rest of you where it came from.
I said it once, and x is
Do you all see it?
Yes.
So this is really, f of 3 halves is actually 16 minus 3 halves squared, square rooted.
So it'd be 9, 4, 6.
So the volume of this, I'm going to call this rectangle number 2, where this would be 1, 2, 3, 4, and this would be rectangle negative 1. No, I'm just saying, I want to look at these. So if I want to know the volume of rectangle number 2, it would be pi times the square root of 16 minus x squared squared
Oh, why is that?
times one.
Pi r squared, got it.
So R is the function.
Does that make any sense to you?
Yes.
And so you would figure that out, and that would be the volume of that particularly sliced cylinder, that short little cylinder.
Do that.
We would have to do that,
What's that square root?
we would have to do that 4 times and then double,
Times 2.
because we do the same thing on the
So
back
can we do
half.
that in our
It's symmetrical.
Riemann?
Can you?
What is it called?
Because Riemann only does areas.
Riemann.
Well, we just have to
Yes, we can do that.
double it.
Can you do that?
Yeah.
Well, we
Try.
couldn't actually graph the whole, we'd only be able to graph here. And so
Graph
Just see if you can make it work for you and make Riemann the program work for you to do this. So that you can get the total estimated volume of the sphere. See if you can do it.
Square.
Yes.
Endpoint. Wait, would we do, what would we do as an endpoint?
Yeah, you can see the problem, right?
Wait.
That's all right, keep working on it.
I'm gonna do 0 and 4 as endpoints.
Oh, wow.
Riemann is designed to find areas, not volumes, so you're gonna have to do something. You have to think harder about how you're gonna make Riemann work for you. And you
If
can
we
do
can
it.
make our area seem, our volume seem like an area and trick Riemann.
You go ahead and see what you can trick Riemann into doing and make sure you get the right answer. And if you don't, then we'll just talk about it together. But you can try it, give it a shot.
I got 12.7, that's not right.
It doesn't must square to a cube, right?
I got, it's like 40, whatever.
0. What is the y equals 16 minus x. It's all around one.
My partition's 8.
Oh, wait. I
You got 50.
got 270.17.
That's not right.
I was dang near close.
Our actual rate is,
You got 260 what?
270.176.
Yep, then you did it right.
Wait, what? What'd you do differently? What did you do? I just did it right here. We had to try it. I did the same thing. I did exactly that. Over here, Raymond. So I just did Riemann.
Riemann.
One. I got half of it. See, I did 0. Okay, so you got half of it.
That's excellent if you got half of it, because now you do double.
4. 8.
That's more slowly.
8 y 8.
Okay,
Oh yeah, okay, yeah. That still doesn't look like mine though. Your function is different than mine.
What's your
What are you guys putting in for your function? Don't you just put in that?
Yeah.
Look at my function.
What do you do?
You do not put that into your function, I'm afraid.
You know, I put the V2 in
You
there.
put the pi.
Well, let me tell you this. This particular one will work because this is a 1. If that partition were not a 1.
You put exactly what you put as V2. V2 is what you put in line 1.
Because
So what I want you to do,
Wait, times pi?
after you've gotten, have y'all gotten this answer that he got? Okay, we'll keep working on that. Then if you think you know what you're doing, you can try it for 16 slices instead of 8. You should try that.
I pictured it look like that.
Well, what's your Y function?
What do you go?
As
Why
in
do you use
increasing the accuracy?
No, it's not, it is.
Why is it not?
I just did it as
Because it's
what'd
V2.
you put for your
Why is it V2?
You're trying to get the whole sphere, not just the little rectangle. You're trying to get like one rectangle.
Just say you're bound for making.
You are getting the area of this circle rather than the sphere.
Okay.
You're calculating the circle. You're supposed to calculate the sphere. So you add in the pi and the square. And technically this, but that doesn't matter if it's 1.
I'm confused as to why sticking like a 6 in there would mess it up.
What?
Hang on to that thought.
Is there an example I can look at?
Wait, it's
Why sticking a what in there?
1.17.
A
Well,
6
she
square.
says we can
That's
only plug in
close.
V2
Did you
because
use
it's a
MRAP?
1 there as
Yeah.
opposed to like a 7.
That's correct.
Okay. Should we
And that's really close to the 268, which is the true
Well,
value.
because then you would just plug in a 7 right there.
So even with only 8 slices, it's pretty good.
So now what, and you do 12?
No, 16. See if you can do it into 16 partitions, see if you can find the volume.
Why?
Would you have to change your radius function if
No,
height was different?
I just did change in, you can, there's
Why do you
options.
use
I got
268.6?
No, I'm not confused about the same thing you were.
Huh?
We're not doing the same thing.
Why do you use not the function for the circle though?
Okay, I got 270.1.
Because we're trying to find the volume of cylinders now. And we need a
Now how
volume,
do we get-
we have a volume of cylinders formula. We're finding cylinders, I sure those cylinders are those two things. We're finding the volume of the cylinder and adding them up.
So you got it though?
So what would you be finding if you found?
I want to do 16 cylinders, so they're really short. I'm gonna add
How
those.
do we get?
What would, if you
Why-
use, y equals.
why is there-
Riemann, what would
Why are we
you
using
find?
Why was 16?
No, if you just use the y equals
V2?
16 minus.
I'm not sure how you plugged in your equation for the radius, plugged in your height.
We just find the area.
So for
and
16,
Oh, so we plug the Y
That would just, yeah, that would just be area.
Because our
That would be
y's
the
are
area of each circle belonging to
Okay.
the cylinder.
I don't think.
So are you able to make it work or not?
Where's the point of confusion?
In the one or the delta x.
Our 1 is our height.
What do you have in y1?
I have pi.
I
have V2.
X squared.
You have the square root, I'm sorry, you have pi
Well, I actually
pi
did
times,
pi times parentheses the square root of 16 minus x
You
squared
don't need the square root,
Squared.
you can just cancel
I
the
know,
square root.
I
and
know.
squared.
times 1. Well,
Yeah,
times
I-
7 currently. Times whatever.
if you were doing 16 partitions, you'd be multiplying by,
What?
if you're doing 16 cylinders, you would, this number here would be,
1/2.
okay, and did you put 1/2 in the formula?
No. We only did 8 partitions.
No, then
I'm
I,
asking you to do
I did-
16.
Oh, you want us to?
I did 16
Oh,
and I
16
got
partitions, you have to change
68.6.
That's correct.
Like I did.
Why do we have to change it?
I'm so.
Let's discuss that if you're willing. I don't know if you guys are ready for me to
Yes.
teach you yet or not. You're still,
Why?
Because if you do 16, it changes
So is
the
1 our
partition.
height there?
If you do 16 partitions, it changes the length of each of them from 1 to 1/2. So you have
yes,
to put
so the
1/2.
height of your cylinder, when you pull that out, the height of the cylinder.
Oh, so that's our height
tall.
side.
I didn't put one in and I got 268 when I did 16 partitions.
Yeah, so
why did you leave the 1/2?
Lousy.
Because it was just 1?
Yeah.
Okay,
Yeah, I just left it out.
so that means that now we have to put the 1/2 in. What are you getting?
Wait, I didn't put the one.
I didn't put the
I know, be quiet a minute. Just
Yes,
hang
you
on.
wrote. That's weird.
Now that we're doing 16, that height of each cylinder has now got to be 1/2. Do you understand where the 1/2 comes from?
Yeah.
Because we're going from 4 to 4, Sonny, which is, if I do 8 partitions, they're each 1 wide. If I do 16, they're each a half wide. So then when I pull that out, it's only half as tall. This is the tall part. You see? Will it get you the right answer when you put 1/2 in there?
No.
That's the crux of it. That's what I'm trying to get
I
at.
just got it figured out.
I know he does.
Yes. For the first time, I've got it figured out.
It gives me 134 as opposed to,
Right.
which is half of what it should be. So just don't stick a half in.
There's twice as many partitions to add up. Because you're basically.
You just got to somehow build the 16 parts in there. It's got to be built in there somewhere.
So do you just times it by 2?
Yeah. And then it
Because
cancels out the.
you're saying you have half as, your partitions are half as big, but you have 2 times, so it cancels out and there's always 1.
All right.
If
This
you
is
had
what I am suggesting, folks.
32, you times by 4.
This, if it were 50, you'd have to figure that out, but you could do it. It's a fraction. What you were saying is
So
true.
why doesn't Raymond work like that?
This part right here. This is the area of the circles at the bottom of each cylinder or the top, right?
Yeah.
That is 2-dimensional. So is any function that you deal with Riemann, 2-dimensional. This part right here, this is f of xi. This is delta x. And this part right here, which is a half if you're doing 16, that part right there is all built into the number 16 when you put n equals 16 in your partitions. If you tell it you're going from -4 to 4, and the 4 is right here, it knows that, I mean, that's what it means. The radius is 4, and if you're gonna split it up into 16 pieces and you tell it, let n equal 16, it will automatically make each partition a half and deal with it.
So Riemann doesn't care about your.
This is your delta x. And that, right, all these are all tied together. Your n values all tied together. But only the two-dimensional part of the cylinder, not the extra third dimension, which is the height. That's in the partitions. This should be what you put in for y1. And this is when you write n equals 16 in the program, will automatically build that in because it has to do with partition lengths.
So we just have to tell it,
So then, do you have to put delta x in Riemann anytime you use it?
Riemann will account for delta x automatically when you tell it n is 16
So you
or
always-
50 or whatever. It automatically figures this part out.
so we
The
just
size
have
of
to
the
find
partitions.
So we
how
always
long,
treat.
we don't have to figure slices.
We always treat delta
Right,
x as.
you don't have to
one
put
if
the
we're
width
using
into your
Riemann.
formula, because if you do, if you put 1/2 right here, you'll end up short.
For a three-dimensional figure.
When you're doing volume
What
using
about
Riemann, you've got to
four-dimensional
force the two-dimensional in this, and the third dimension, you gotta understand what's going on.
Oh.
You understand that, Kylie? Yeah? So do it again, and leave your f of x, instead of what you had the first time, just leave it, pi times the square root of 16 minus x squared. Stop. That's the two-dimensional part. Do the Riemann on that y1. And when you tell it that the partition number is 16, it will automatically make each width a half.
So how does it convert
So
it to
Riemann will
2p
calculate
to
this
3d?
So does this 6?
By adding this extra dimension right here, it will find, this will find a sum, when you, Riemann will sum up the areas of each circle at the bottom of each cylinder. And then it will take each of those areas times the partition width, which you told it when you said there were 16.
Okay. Got it. That's dope.
Okay, so now I'm gonna run it, see if you can get it. With 16, you run the Riemann. And you already have it in y1, so continue. I'm just talking out loud. Keep thinking out loud. Draw pictures, yes. Endpoint 0. No, I'll say endpoint -4. Right endpoint 4. And midpoint rectangle, is that what we're gonna do? Midpoints? N is 16.
Here's the trapezoid, this way.
What did you do for your 16?
What's the real area of this sphere?
368 or something. 368.08 or something.
268.
Oh, 268, yeah.
With trapezoid, it's not that good. I got 267.
That's what I got here. On how many ends? 16.
16.
I got 267 around 3 times.
Yeah, that's what I got. I guess midpoint is better with this.
And then no trapezoid there.
They just draw the secant line.
So did you remember seeing the pictures? It looked like it belonged to some sort of upturned parabola shape.
Yeah.
Why wasn't it spherical?
Because it adds that, it basically shifts the whole thing up.
Really? There,
Because it fits the graph.
Because it adds
it fits
them
the graph.
onto each other.
so you're saying that that's a distorted circle?
Yeah.
It's not.
No, that's not what I'm saying.
That's what I'm saying.
That graph that it drew for you is the function, this one.
Yeah.
This function right here, which is a function of gathering of circles, not a circle.
Square though.
Yeah, square,
Yeah, okay. I see square.
yes, square. Say that again. So it should not be circular, because this is what it's graphing. It's graphing y values that belong to this function, which is not a circle. It graphs as a something that's not spherical, but or even circular. But anyway, with 16 and a midpoint, you get 268.606, when the true value is 268.08 or something. Is that right?
Yeah.
Do you all understand the role of the partitions in adding a third dimension?
I think so. When we're using Riemann, we don't need to put delta x because it will account for that by itself in the partition.
Yes, because Riemann sums up two-dimensional rectangles.
Right.
So you need the two-dimensional, it will add the third dimension when it figures out the width of each partition based on this. Okay, this adds your third dimension, which puts the volume in it.
But if we were to do this by hand, we would need delta x.
Yes, in each rectangle. Well, you would do that function right there and then multiply it by the height of the cylinder. That adds your third dimension in. So if you were doing it by hand, I would just factor the 1/2 out. It'd be 1/2 times, and then there'd be all your two-dimensional stuff. Kind of looks like that. Okay, but you don't put it in the Y1 with it. How are we doing? Are you okay on this or not? You think? You got some sort of conceptual understanding?
Some sort of, so if we don't start there.
Okay, I want to talk to you about the last example. We may not get clear through it, but I want to talk to you about it. Quite often, believe it or not, and I mean, when they teach you about this in a calculus book, this kind of thing, they almost always give you a function to work with. Is it something you're familiar with? You know what the shapes of them look like, things like that. But there are a lot of graphs out there that don't have a function. But they can tell because they've gathered a bunch of data and they've plotted the points and they strung it together. And it doesn't have a particular function that you know of. There may be one, but it doesn't have a particular one. Take a look, for example, at the cardiac output graph on page 268. What we've got here is a doctor that would like to figure out if his patient is having cardiac problems or his heart is not pumping as efficiently as it should, knowing that a healthy heart does a certain thing. Now listen to the words. The number of liters of blood your heart pumps in a fixed time interval is called your cardiac output. For a person at rest, the rate might be 5 or 6 liters per minute. That's about 1.5 gallons per minute without a heart. That old heart's a pretty good pump. For the size of it, okay. During strenuous exercise, the rate might be as high as 30. That's practically 8 gallons per minute.
It's pumping that
blood.
through your body.
Pumping it through your heart, gathering, it pumps it through your cardiopulmonary system, grabs the oxygen, goes feeds your muscles, depletes it, comes back, and all of that, the amount of fluid pumped through your heart to do that in 1 minute, if you're doing strenuous exercise, is practically 8 gallons. That's a lot. That's a lot. Your heart's an amazing thing. Okay. So it might also, your heart rate or your cardiac output might also be altered by disease of your heart or some other thing in your body that causes it to not function as efficiently as it should. Here's what it says. How can a physician measure a patient's cardiac output without interrupting the flow of blood? That's a nice way of saying without doing invasive surgery, cutting your ulna vena, coming up back to your heart, dumping it into a bucket for a minute and measuring it and then reattaching it. That would be the direct way of measuring it. It would probably kill you. Okay? Especially if you weren't transfusing blood somewhere else. I mean, you know what I'm saying?
Yeah.
That's a very invasive way of doing it. And that's what the guy's saying. Without interrupting the flow of blood. Here's the technique. Listen. One technique is to inject a dye. It's usually radioactive. That should not bother you. Radioactivity should seldom bother you. Okay. Inject a dye, which is usually radioactive, into a main vein near the heart. Do it right in your ulna vena cava. Y'all know where your ulna vena cava is, right?
No.
It's the great big vein that everything dumps into that goes into your heart that's deoxygenated. Goes into your heart, comes out the aorta, which is now full of blood. What comes out of your cardiopulmonary system and heads out to your body again, comes out in a great big old hose that's got oxygenated blood. That's the reason why when you see a diagram of your cardiac or your whole venous system, the blue ones are blood that's headed back to your heart, and the red ones are ones headed away from your heart because they've been oxygenated, and that's what causes your blood to go from blue to red. The hemoglobin takes in oxygen, turns red. You with me? Okay. By the way, when they go over to the plasma center and they stick that thing in your arm, the blood doesn't look red or blue. It looks almost black, but it's blue. It's blue because they're taking it out of a vein which has depleted its oxygen, is headed back to your heart, and they interrupt that and take it out and put it in a jar.
Is it actually blue though?
But it is in the tube because it hasn't hit any oxygen yet. But when it hits that jar and there's oxygen present so that it can fill it up, you know how the air has to be pushed out of it as the blood goes into it? It's exposed to air and it turns red. Bright red. It's really cool.
But Like
But when it's deoxygenated, it actually is blue.
19
Well, it's
something.
closer to blue than red. It's dark, it's really, really dark. Because hemoglobin, when it picks up oxygen, turns red. Okay, listen up. So we've got this radioactive dye they pump into the vein just before it enters your heart. So that as soon as it enters your heart, they start keeping track of how much of that dye they put in you is being kicked out. You see?
Oh, yes.
Okay.
Wait, so they put a dye in deoxygenated blood, and then it would go through, and by the time that dye gets oxygenated.
Through the heart, they figure out
that-
how, yeah, based on a mixing of blood in your heart. I mean, your heart's squished, just going like this.
Yeah.
And as it mixes the dye with the blood, they can measure how much of the dye is coming out the back end and be able to figure cardiac output. If you know what you're doing. And that's what we're gonna learn.
I don't.
So listen up. We're gonna run out of time before we get done here, but I want you to think about this. Please don't read the solution. I want you guys to come up with this together tomorrow, okay? So it says, where the concentration of dye can be measured every few seconds, usually with a Geiger counter of some kind. They measure the radioactivity as it comes out the other side. Unless you are in like an MRI and they can actually see the dye coming out, but that's still a very thing to measure, whereas you can actually count radioactive atoms coming out of your heart if you have a Geiger counter. Okay? As the blood flows past, it counts these things, and the plot obtained from the data shows the response of a healthy resting patient to an injection of 5.6 milligrams of dye. That will become important tomorrow. Please don't read this. You can get started on the exercises, but don't read the solution to this cardiac problem. It's kind of cool when you see how it comes out. Okay? Please don't knock my computer off on the way out. Grab it right now, just in case. Okay, we're all done for today. Bye.